Everybody did this? No. Yeah.
What's X and Y?
What's that?
What'd you put in X and Y?
X, I put time here. Oh, okay. So for series name, I put measured data, but X, I put this data.
What's the difference
Which
between
one's
series 1 and 2?
Okay, so
L. Column L.
let me edit this one. So if you look at this, this is the one, x-axis is these, and the y-axis is this. For the other one, other series, x-axis is the same x-axis, but y-axis is the fit. So I'm comparing measured versus fit. One of them is an equation, this equation, sigmoid equation. One of them is sigmoid equation. The other is actual measured data that we input. We are trying to find these delta, alpha, beta, and gamma that will give the same numbers or similar numbers as this one, right? Okay, so how do we find a fit here? I can change this delta. See what happens when I change delta. It's 2 now. If I make it 3, see what happens. It goes up. Okay. If I put 2.5, it goes down. This looks like a pretty good fit. Not good enough. Okay. I can do all day 3.5. Right? Alpha. I can change this, and we can do all this. Of course, we don't do that. What we do is we use solver. How many of you have the solver under, if you go to data, here, solver? None of you? Okay, so this one doesn't have it either. You can see if you go under data, it's not there. So what we will do is go to File, Options, Add in. You see Excel add-in, go, you'll see solver add-in. Click there and say OK. When you do that, you can see the solver will show up under this analysis. You got it? Okay. Now got everything? Okay, so we'll use that in a minute, but we are not done yet. So what I want is, let's find the percent error between this and this. So what I'd like to do is equal now equals absolute value, ABS, the difference between this and this. Now what I'd like to do is I'd like to take the logarithm of fit minus logarithm of the measured. The reason is because we always plot everything in log-log space, and we always look at these graphs in log-log space, so it's better to find the difference in log-log space. So that's why I'm looking at the difference between absolute value, logarithm of fit minus logarithm of the measured. That's the amount of error, divided by, let's say we want a percent error relative to logarithm of, let's say, the measured value. That's our reference. So essentially, absolute value of the difference between these two divided by the measured value. That's our reference. So that's our percent error. If you enter, you would get 17.5% error. If you drag and drop all the way down, you will see a whole bunch of errors, difference between. So there's about 17% error between these two. And if we sum up all the errors, that will be the total error. So this is the total error that we want to minimize. Everybody with me so far?
Can you go back to that?
No? This equation?
Yeah.
Okay, so if you look at this, absolute value of logarithm of T21, which is the fit, minus logarithm of L21, which is the measured E star for this row, divided by logarithm of L21, which is the logarithm of the original E star.
So you're just
It's like a percent error between those two, except we are all taking the logarithm of individual numbers. Good? You have two computers?
Yeah.
Is that absolute value of everything then?
No, doesn't matter, but absolute value of only the difference.
Yeah, that's fine.
Okay, so absolute value of the difference. Did it work? Anybody got it working?
Did you change the, he changed his alpha parameter to 3.5.
Oh, that's right. I didn't
So-
do that.
Okay, what was it, 4? 10.1? Okay, cool. So now what we'll do is we'll run solver. So let's click on this solver. This is the window that will show up. Set objective. So my objective is to minimize this total error. Select the cell U41. And I want that to be 0. I don't want any error. Let's say to the value of 0. By changing variables. By changing all these variables. I want you to change all various C, delta, alpha, beta, and gamma. Vary all these variables to minimize this so that I have a fit. Okay? Everybody with me so far? Click solve. Solved. Okay. See all these numbers changed. Look at the fit. Can you see the fit? You can't because it's behind. It's a perfect, very good fit. Okay, so you have a very good fit of the data. So now what it means, if you look at the numbers, they're pretty close with a small difference between fit and equation. So now we have an equation for E star as a function of temperature and time. C is going to allow us to convert time to reduce time, and then this is going to calculate. So why is it so valuable? Because this curve is independent of temperature, independent of frequency. So let's say we are talking about a road. If you go with depth, remember for a given speed, let's say vehicle speed limit is constant, but with depth, the frequency is going to change. So with depth, you're going to have different frequencies, and temperature will change daily and hourly. So as the temperature changes, we can calculate the E star at different temperatures and at different depths. We can calculate E star at different temperatures and at different depths. That's what the Mepdg Pavement ME does. So it uses this equation, calibrated equation now, it's solved for these, just like we have done here, and finds the E star at different temperatures, depending on the climate data available, and finds the E star for each layer, and uses that E star computed by using this in structural analysis. That's my E star. We were entering 1 million and 1.1, 200,000 in the morning, right? So that comes from this value. So these values are input to the Julia to find the stresses. Clear?
The same technique is used to find G star yesterday, by the way.
Yeah, that's true.
To
That's,
fit the G star curve finder uses the same technique.
yeah, so the same technique is used to calculate the G star master curve of the binders also, except there are a few differences. So we don't really go to viscosity, we just work only with the G stars only. Okay? All right, so what's that?
Which cells are the variable cells?
C, delta, alpha, beta, and gamma.
Okay, I just want to make sure.
Those are the variables. Those are the data points. Now you have an Excel sheet that you can do dynamic modulus master curve, which is a valuable thing to have. So, you can, if you have, when you run a pavement ME, you can just put your inputs in there and then see if this works. And we did that. We did compare against these numbers, is alpha, beta, and delta, compared against the pavement ME output, and they do match. So you can do that yourself. With small differences, there are some small differences, but that is because the solver, you can have different combinations of these variables to get to the same number. So those differences are not very significant. It'll give you the same number. Yes?
Sorry, just to be clear, could you go back to your solver one last time?
Yes.
So what is
Objective is this error,
Oh, okay.
and I want this to be 0 by changing variables C, delta, alpha, beta, and gamma. And solve. Done.
And
Yeah.
what method are you using there on the solver?
Oh, GRG nonlinear.
Okay.
Didn't work for you, or?
I have an error in my portal for error.
Look carefully.
So it's just giving me value right here.
Can you double click? No, you need, that's the sum. You need to sum. This is the total error of all this.
Yeah.
Oh.
Mhm.
Just right. Oh, there it goes.
Right.
Oh.
Okay, and now do the solver.
Yeah, okay, I got you.
Perfect.
Yeah, so I was trying to do the solver for all of them, but it only does a single value.
That's usually works better that way. Yes. Yes.
So the default values for those variables, were those arbitrary?
Good question. They are not that arbitrary. If you do this from scratch, you know nothing. If those cells are empty, good luck. Yeah, so this is a simplest optimization solver, Excel. So you need to be close to the target, well, in the same ballpark. If you put 5,000 in one of them and 1 million in the other one, it won't solve it for you. You need to be within.
When you start, you can change the number. You can see the one curve walking towards the other.
Exactly. That's exactly what I do. I always enter then manually, try to get it close visually. You know, if it's just close, at least you can see it within the screen. Then you run it and you'll find it.
How many times can you run the solver to keep reducing your error?
You can run many times. It shouldn't be keep reducing the error, really. Did it reduce the error when I tried
It won't
again?
reduce it any further.
It won't.
It won't. No. So yeah, it's the I run it again.
It might change the variables again, but it'll still come up with the same error.
Yeah. So this is in MATLAB is a software that I use a lot. I actually developed that visual pave software in MATLAB that has much more complicated, much more accurate optimization tools that can give you better fits. But in case you're not satisfied with some of the fits, you can consider using MATLAB in the future. All right, so I'm going to continue if everybody is okay with this exercise.